In the arid southwest of the United States and western Mexico, the North American monsoon is a critical component of the regional hydroclimate that the North American monsoon provides a significant and critical portion of the annual precipitation for these regions in July, August, and September, but are otherwise relatively dry during other seasons. Mean monthly precipitation histograms for select locations across the United States shows the contrast of the summer peak precipitation for Arizona compared to the almost non-existent baseline precipitation throughout the year. Although other areas of the country have summer peaks as well, they often have a strong baseline precipitation through the year or have more than one peak, which helps sustain the respective ecosystem, so it is not as dependent on the summer rain as Arizona is. Replenishes water resources and revitalizes the desert to become hospitable again after hot summer temperatures. A comparison of the mean seasonal precipitation during the monsoon season to the annual total precipitation of North America shows that for southwestern North America, anywhere between 50 to 70% of the annual precipitation occurs during the monsoon season. The ecosystem relies on the North American monsoon as a water supply for fauna, wildlife, replenishing waterways, and recharging desert aquifers. According to one study, nearly 25% of the rainfall from monsoon storms was retained in streambeds and percolated to groundwater storage. Society in this region also greatly relies on the monsoon precipitation for agriculture, livestock, water supply, recreational activities, and other economic concerns. So what causes the North American monsoon? The monsoon is caused by seasonal reversal of wind direction due to differential heating between land mass and ocean in the tropics. Hot temperatures and dry air create a thermally induced area of low pressure over southwestern North America, which couples with high pressure in the upper atmosphere over the Midwest and cooler air over the Gulf of California to drive the North American monsoon. The lower pressure gradient results in a weakening of the southwesterly winds and allows a transition to southerly winds to transport moisture from the Gulf of California and forms an upper atmosphere level cyclone over southwest North America. While atmospheric circulation controls the distribution of water vapor, the tendency to form thunderstorms and the temporal distribution of the convective activity depends on local topographic effects. The topography of southwest North America aligns with the higher precipitation rates after the onset of the monsoon. Although the driving factors for the monsoon onset appear relatively simple, the monsoon is affected by seasonal and longer timescales of complex interactions between both the Pacific and Atlantic Oceans, atmosphere, and landmass. Even though the North American monsoon is best known for its influence on the southwest hydroclimate, it affects the hydroclimate of the Midwest and East Coast. Evolution of the vertical structure of moisture transport immediately prior to and after the onset of the monsoon shows the formation of the North American monsoon anticyclone, and the effects on the Midwest, which causes dry air conditions, and the East Coast, which creates a trough and makes wet conditions. The onset of the North American monsoon begins in mid-June in Mexico, and the monsoon rapidly transports north such that the onset is at the beginning of July in Arizona. This figure shows histograms of the mean daily and 5-day running mean precipitation during May through August at locations in the southwestern United States and Mexico. It shows that the onset in Mexico is often in June and later in July further north. It also demonstrates that there's greater precipitation closer to the ocean in Mexico, and this effect peters out to the north. One of the major concerns of climate change is how it will impact local and regional hydroclimate. Studies have found that as temperatures increase, the prevalence and duration of drought will also increase. Additionally, climate models have shown that warmer air will allow more moisture to be retained in the atmosphere and will result in a shift in jet streams northward and result in an increase in frequency of severe storms. A recent study in southeastern Arizona used a dense network of rain gauges to monitor the local convective variability of the monsoon thunderstorms. Their results did confirm the monsoon storms were intensifying, and it made headlines this summer. One glance at the standardized anomaly of temperature for Arizona shows why Arizonans are so concerned about climate change and how it will affect them, as temperature anomalies have been increasing over the past 3 decades significantly.